today's lecture we continue the discussion on production flow analysis. In the last lecture we completed the exercise of creating machine cells and part families for a 16 by 43 matrix which had 16 machine types and 43 parts. We obtained a final solution like this, where we created 5 cells. This is one cell, second, third, fourth and fifth, and we also said that machines 6 and 8 will have to be duplicated to each of these cells depending on the requirement, and if there are sufficient numbers of 6 and 8, then the solution has 2 intercell moves which are given by the ones which are in red color, where component number 2 moves to another cell to visit machine number 14 and component number 9 moves to another cell to visit machine number 11. Now we have also seen that there are 3 aspects to production flow analysis. One is called factory flow analysis, group analysis and line analysis. This solution is something that we obtain at the end of group analysis, and after this solution we have to look at line analysis. So in line analysis we try and bring in many things that we have not considered during the group analysis. For example, when we started describing the data for group analysis, we used a matrix similar to this, but the matrix whose rows were 1 to 16 in that order and whose components were 1 to 43 in the given order. So otherwise the matrix is similar. So when we introduced the matrix, we also said that this matrix captures only the incident data, which means it captures data of visit of components on the machines and does not capture data relating to volume of production of these components, the processing times as well as the sequence in which they visit the machines. So now when we start creating or planning the required capacity of each of these cells that have been created, now we have to find out whether one machine is enough to meet the demand of all the components visiting that particular cell, or do we need more than one machine of a type simply because of the capacity requirements. In other words, capacity requirements have to be calculated based on which the number of machines of a particular type going to a cell will be determined. Once again, if we look at the first cell which has 1, 2, 9, 16, and if we assume that 6 and 8 are also duplicated, so this cell will have 1, 2, 6, 8, 9 and 16 as 6 machines, and it will make these components starting from 2 and so on to 42. 2, 4, 10, 18, 28, 32, 37, 38, 40 and 42 are the components made in this. Now we have to do based on capacity calculations whether one number of this machine is enough or whether more than one number of this machine is required. So we have to do that capacity calculation. Secondly, the sequence of visits is also not known, and the cell invariably has products moving in a unidirectional flow. So either if there are reentrant flows, or if we have a situation where the route or the order of visiting the machine changes the requirement, we may have to add machines into this cell. So line layout addresses all these issues, and we will now see how we address some of these issues through some examples. Now we want to find out what is the requirement of the number of machines in a particular cell. So we now say that, for example, if we take this cell and say part number 2, So, if we take part number 2 into this cell, now part number 2 visits machines 2, 9, 16, 6 and 8. It visits machine 14 in some other cell. So, let us not look at that. So, let us look at 2, 9, 16, 6 and 8. If we start looking at the first cell, we have machines 1, 2, 9, 16, 6 and 8, and if we take machine number 1, only 2 components 37 and 42 visit machine number 1. So, what is the requirement on machine 1 in cell 1 due to component numbers 37 and 42? So, we describe this that way. If volume of part j per year is equal to dj. Now, if we take part number 37, then the volume will be d37. Unit processing time be Pij. So, Pij will be the processing time associated with processing part number 37 on machine number 1. So, the time required in machine I per year for part j is equal to Pij into dj. Multiply the unit processing time by the demand or volume of production would give us Pij into dj. Now, let the time available on machine I per year is Ai. So, if the organization works 6 days a week and for 16 hours a day, then the time available per year is 6 into 16 into 52, which is 4992 hours. Now, the availability, which is Ai, is now taken as k times 4992, where k can be 70 to 80% and includes setup times and non available times. So, let me explain this further. So, let us take the case of cell 1, which has components 37 and 42, which also has components 37, 42. Cell 1 has machine number 1 that has components 37 and 42 visiting. So, what is the load on machine 1 in cell 1? So, load on machine 1 in cell 1 is equal to D37, which is the demand or volume of component number 37, multiplied by unit processing time, which will be the processing time for component number 37 on machine number 1. Now, total load plus D42 into P 1, 42. So, if more than these two components are visiting this machine, then we have to add all of these. So, now this load will be, we can be called as sigma dj Pij as load on machine I in some cell k, summed over parts j. Now, let us say we are looking at machine number 1 and say if we work 52 weeks into 6 days a week into 16 hours a day, we have 4992 hours available in a year. Now, we cannot say that all the 4992 is available, because there can be so many reasons. If we see that this 4992 ideally should be used for processing as well as setup times on the machine. So, this has a setup time component. This some of a large proportion of this will be used to meet this requirement, but some time out of this 4992 is also used in setting up the machine to manufacture the parts. Sometimes setup time component can be, if I take this 37, so D37 divided by, there will be a batch size in which we will be making this 37. So, that will be called as B37 into setup time S 1, 37, which means this is the number of batches that we will make, or the number of times we will make this component 37. At every time we make this component 37, there is a setup time. So, this will be the setup component, plus, or if I take out the summation, then I will do plus D42 by B42 into S 142. So, this will be the total setup time required. So, this 4992 can be used as for setup plus processing plus others. Now, this others would include sometimes machine waiting due to scheduling related issues, sometimes due to availability issues. There could be a breakdown, there could be part not available, operator not available, consumables not available, and other issues. So, many times all these are factored, and we could say that about 10% is lost in these. Sometimes it is possible to accurately estimate this, sometimes it is not possible to accurately estimate this, because this batch size can also change with demand and time. So, this is, even though it is a constant and can be measured, the batch size changes, and therefore, this also cannot be measured very accurately, considering a time frame like 1 year and so on. It is very hard to say how many times we are going to make this in 1 year. Therefore, this sometimes it is difficult to measure this one completely accurately. So, it is customary to say that this plus setup, the whole thing would take something like 20% to 25% of the times. So, the organization, based on experience and based on some of these computations, would say that about 75% of this 4992 would be made available completely for processing. Sometimes it could be 80% and so on, depending on new machines, depending on less time lost due to some of these. If we have good scheduling practices, if good maintenance practices, then the availability will increase up to 85%, 90% and so on. So, it is possible to find out what percentage of this 4992 is actually available. So, now what we will do is, let us call that availability by a certain number k. So, k is between 0 and 1. So, if it is 90%, then it will be 0.9. So, now this amount of k into 4992 should be able to meet this requirement of D37 into P137 plus D42, because this is the load or processing time requirement of this. So, at an aggregate level, one would say that this quantity divided by k into 4992, if it is less than 1, then we say it is enough to have one machine in that cell. Now, if this quantity, the load divided by availability is say 1.5 or 1.6, then we will say that 2 machines are required in that cell. Alternately, we can even individually calculate and say D37 into this quantity alone divided by k into 4992 will tell us how many equivalent machine loads is required to make this. How many equivalent machine loads is made for this? For example, if this is 0.4 and this is 0.3, then we could say a total of 0.7 is required. So, with one machine it is possible to do. If this is 0.7 and this is 0.6, then we say it is 1.3. So, with one machine it is not possible to do. So, we include 2 machines into the analysis. So, this is what we have tried to explain through this as some kind of an AIJ. Now, AIJ will be the load by the jth load in terms of equivalent machine loads by component or part j on machine I in a given cell k. So, that is our AIJ that is given here. So, we can calculate this and try to find out how many machines are required of each machine type in each cell. So, that is one form of doing line analysis. Now, the other thing that we would look at is what is the effect of unidirectional flow on the cell. Now, in order to explain this unidirectional flow, we take a different example. We have not taken the same example, we take a different example. We take a smaller machine component incidence matrix with 6 machines and 8 parts for the purpose of illustration. We take a much smaller example. So, this is the given machine component incidence matrix, and let us say we are making cells from this. So, let us say 2 cells have been made from this machine component incidence data, where one cell has machines 3, 1, 4 and 6, that makes parts 1, 4, 5 and 6, 1, 4, 5 and 6. It has 3, 1, 4 and 6, and a second cell has 2, 5, 6 and 2, 3, 7, 8. So, there are 2 cells. Now, this is a different example. This is not part of our 16 machine 43 component example. It is a much smaller example of an incidence matrix, more for the purpose of illustration. So, the incidence matrix itself has 6 machine types and makes 8 parts, and let us say at the end of an exercise like production flow analysis, we have got 2 cells or 2 groups which make this. Now, let us go back and see how the 2 cells are going to be laid out. The first cell has machines 3, 1, 4, 5 and 6, and the second cell has machines 2, 5 and 6. Now, you realize that this picture has 2 machines of 1 and 2 machines of 4, and this has 2 machines of 6. Let us assume we start with 1 machine of each type. We will have 1, 3, 4, 5 and 6 that are here, and 2, 5 and 6 which are in the other one. Now, let us take each of these parts. So, part 1, the sequence is machine 1 and then 3 and then 4 and then 6. These numbers represent the sequence or order of visit of the parts on the machines. Now, the machine component incidence matrix is created in such a manner that it is not a binary matrix, it is not a 0 1 matrix. We are capturing the incidence data. For example, this component visits this machine, this component does not visit machine 2. So, incidence data is captured, volume and processing time data are not captured, but the order of visiting the machines or the sequence of machines is captured. So, we say that part number 1 visits machines 1, 3, 4 and 6 in the order 1, 3, 4 and 6, whereas component number 8 visits machines 2, 5 and 6, but in the order 6 first, followed by 2 and then followed by 5. So, with this additional information of the order of visit of the machines, let us go back and see how our cell will look like. Now, for part 1 it visits 1, 3, 4 and 6. So, you realize part 1 it visits 1, 3, 4 and 6 and part 1 comes out. Now, look at the second one, which is part 4. Part 4 visits in the order 1, 3 and 6. So, part 4 visits in the order 1, 3, 6 and part 4 comes out. Now, look at the third one, part 5. Part 5 is 4, 1 and 5. So, you see 4, 1, so 4, 1 and 5. So, we assume that machine number 5 is brought into this cell, it is duplicated. So, 4, 1 and then 5, you can see from 4, 1 and then 5 it goes out. So, there is an extra 5 that comes into this cell, and then we look at part 6, which has 3, 1, 2 and 4. Now, you see that 3, 1 it goes to 2, it comes back to 4 and then it leaves. So, we could also say for example that 3, 1, 2 and then it could come back to this 4 and it could leave. But the point that we make is, because of unidirectional flows, we may have to increase machines as it comes, because if you see this very carefully, now there is 1, 2, 3, 4 and then you find part 6 which has 3, 1, 2 and 4. So, you cannot have machines 1, 2, 3, 4. If we look at part 1 has 1, 3, 4 and 6, part 6 has 3, 1, 2 and 4. So, there is a part which moves 1 and then 3 and there is another part which moves 3 and then 1. So, if we let this cell have unidirectional flow like this, starting here and going this, there is definitely a need to duplicate machine number 1 in order to maintain unidirectional flow. Similarly, we can do this analysis for the second cell. Second cell has 2, 5 and 6 machines and parts 2, 3, 7, 8. Now, 2, 5 and 6. Now, let us go back to this 2, 3, 7, 8. Part 2, the visit is 2, 5 and 6. So, you could start with 2, 5 and 6, part 2 goes. Now, look at part 3. Part 3 it is 5 and 6. So, it fits in 5 and 6, part 3 goes. Now, we look at part 7, the visit is 2, 5 and 6. So, once again 2, 5 and 6, part 7 is fine. But look at part 8, which is the last part, it is 6 and then 2 and then 3, whereas here it is 2 and then 6. So, this would necessitate that if we want to maintain unidirectional flow, then we have to have another 6 that comes. So, the flow will be in this direction. So, line analysis has multiple components, one of which is to find out extra machines based on machine load, another is to find out extra machines based on the requirement of unidirectional flow. Now, unidirectional flow is required in a cell, so that there is much more control in the cell. If we do not have unidirectional flow and if we let bidirectional flow within the cell, then we will very quickly lose control. So, for this purpose, most situations, whenever we implement a cellular manufacturing, the material movement within the cell is unidirectional. So, to ensure unidirectional flow, it may be necessary to create extra machines in the cell. So, line analysis takes care of all these requirements of machine capacity, number of machines required, the specific layout which ensures unidirectional flow. Let us carry out one more exercise on production flow analysis to try and understand some aspects of PFA which were not addressed in the earlier example. Now, we will take another example and carry out the PFA and try to show the possibility of alternate solutions plus the trade off between intercell moves and duplicating or adding extra machines. So, let us look at this example. This example is one which has 20 parts or components that are being made, which are shown as columns 1 to 20. There are 10 machine types which are A to J. So, the incidence matrix is up to this column 20, 10 rows and 20 columns, and you will observe that the incidence data that we have shown here is slightly different from the two types of data that we have seen. The very first example, we showed a binary matrix which either had a 1 or a 0 and captured the incidence data alone. In this incidence matrix, we had the data as non-binary, but it captured the order of visit of the machines. In this, we said that component number 8 will visit machines 2, 5 and 6, but in the order machine 6 followed by machine 2 followed by machine 5. Now, here we have given numbers like 8, 18, 30 and so on. Now, we have to look at these numbers and say that actually this number is not 10, it is 0.1. This number is not 30, but it is 0.3. This number is not 18, but 0.18. So, the incidence data represents the equivalent machine loads required by this component on that machine. For example, the data that we have here is actually this value that we said. What we have is the equivalent of D37 into P137 divided by K into 4992. For example, this number 8 represents that component number 3 visits machine A and the volume of component number 3 multiplied by the processing times of component number 3 divided by 4992 is 0.08. 8% is 0.08. So, one would say that this component takes 8% of the load of machine A and visits machine A. So, this is another way of representing input data to production flow analysis. Now, we have also added a few things here and said the total load on machine A is the sum of all these numbers in that row and it is 146, which means the total load on machine A is 1.46 equivalent of one machine or 1.46 machine load, and we therefore say that two numbers of machine A is currently available in the functional layout. Similarly, 255 is the requirement on B, which is 2.55 machines, and we say that 3 machines are currently available. 190 or 1.9 is the requirement on C, 2 machines are available. 170 is the requirement on D, 2 machines are available. 100 is the requirement on E, right now 1 machine is available, we will come and discuss about this. 140 is the requirement on F, but only 1 machine is available. The requirement itself says 1.4, but 1 machine is available. 60 on G, one machine is available 90, 50 and 60. Now we have to talk about two things, this 100 load and one machine, 140 load and one machine. Now 100 load and one machine implies that when we have calculated these numbers, we have actually multiplied that 4992 by k, which represents the availability. Otherwise, expecting 100% is very difficult. The k has been factored, or availability has been factored in the denominator when we actually divided. If we had used 4992 and got it, then we should again say that 100% we cannot handle, we will be able to handle only 85% and so on. So right now, because of this 100, one can assume that with one machine we get 100. Even then it is a little tight, but we would continue to assume that this 100 is alright for us. With one machine it is possible to do. But how are we going to explain that the requirement is 140 and there is only one machine available? So we give additional data onto this problem and say that the additional data would say that now E and G, F and I, H and J. So we look at these machine combinations, E and G, F and I, H and J. So we write these combinations, E and G, F and H, F and I, and H and J. So what we are going to say that these machines can be used interchangeably. Which means when required, some load on machine E can be taken up by machine G, some load on machine F can be taken up by machine I, and some load on machine H can be taken up by machine J. So now if we add the loads, we get E and G, the load is 160. If we go back, E and G, the load is 100 plus 60, 160, but then we have one machine here and we have one machine here. Similarly, F and I, the load is 140 plus 50, 190. So we could say that we have one machine of F and one machine of I, some load is shared by I from F. Similarly, H and J, 90 plus 60, we have one machine of each. Therefore we could say that there is enough capacity on the existing system to meet the requirements of the components. Now let us do production flow analysis and see how we make machine groups and part families. So we can do a few things. Now that we have done these load calculations, we can now replace all these loads by 1 and 0 and create a binary matrix which we can use to do production flow analysis. So the binary matrix has been created and the binary matrix looks like this. Now all the loads have been replaced by 1s, which say that this component visits this machine. Now we can carry out the steps of the production flow analysis and we can create the frequency table and we can create the modules. Now let us assume that we have done all that and our frequency table will look like this. The first frequency table will look like this. So we will start with machine number G as the nucleus machine and we will create the first module, the second module, the third module, the fourth module, fifth module, sixth module and seventh module. So there are 7 modules that are created and the 7 modules along with the components look like this. So we will assume that this up to this part we have already carried out, because we have seen in the earlier example as to how to get these modules and how to create the table that has all the modules with the associated machines and components. So, we now assume that this up to this table, the first table we have done by following the steps meticulously, following the steps that were described in the earlier production flow analysis. If you observe very carefully, up to this point the production flow algorithm is reasonably consistent, in the sense that whoever carries out production flow analysis will eventually get up to this table and there will be no difficulties, and all the solutions will be the same till you get this table. Now, after this table we now start merging the modules. We start merging the modules such that if there are two modules where the machine set in one is a subset of another, then we merge both the machine sets and get the superset, and we also combine all the parts and bring all the parts together into one module. So, we have to carry out that. In fact, if we look at that part of the algorithm carefully, a particular subset may be a subset of two other sets, not with reference to this example, but with reference to the previous example. If we had one module, say, which has machines 5 and 6, and above that there is a module with 3, 5, 6, and further above there is another module with 8, 5, 6. Now, this 5, 6 can be merged either with 3, 5, 6 or with 8, 5, 6. So, the merger can create different solutions depending on how we actually merge. So, depending on who is doing it, or depending on the algorithm for the merger or a local rule for the merger, the solution can be different, because the same machine set can be a subset for two other machine sets. Keeping that in mind, we still continue to do this and see whether we can merge. So, when we merge, the first thing that comes to our mind is this ABCD is a subset of ABCD FH, and therefore, this module will merge directly with this and 16 will go to this. So, that is carried out, and then we have these 5 modules, or this goes to this, and then what we do is we look at this 1, 17, 19 module number 7 that has A, B, C, E, and we also said that E and G are interchangeable, which is very specific to this problem. So, we assume now that with the additional condition that E and G are interchangeable or can be used interchangeably, we will now assume that A, B, C, E and A, B, C, G are either one and the same or subsets, and then we add this one also, so that this 13 and 1, 17, 19 gets added to 3, 5, 10 and 12. So, from 7 modules we get 5 modules. So, we now have a solution with 5 modules with A, B, C and G making these set of components, A, B, C, D, F, H and so on. We have 5 modules which come into this solution. Now, after we do this, we carry out one more step where we look at these modules in detail and try to see whether we can either eliminate a module or we can reduce machines in a module by carefully looking at individual modules. So, that we do now, and then we say, using interchangeability of machines, what do we do? Now, F and I are interchangeable, merge modules 3 and 4. Now, B, D, E, I, J, D, E, F, J. So, F and I are interchangeable. So, we again use the interchangeability idea and merge these two modules 4, 9, 14, 20, 2 and 7. So, we do that to get this one. Then we start looking at this module, which has A, B, D, E, F and has 13 and 15. So, go back and see that this is the requirement 13 and 15, A, B, D, E, F. Now, 15 requires B, D and F. So, 15 requires B, D and F. We have B, D and F here. So, 15 goes to module number 2 directly. 13 requires A, E and F. So, 13 goes to module 2 with an intercell move to either G or to E, because E and G can be used interchangeably. So, 13 goes to module 2, but with one intercell move. So, we create one intercell move and we remove this module 5 from here A, B, D, E, F, so that we can remove this module and save 5 machines, and we get a solution which is like this: A, B, C, G, which makes these components, A, B, C, D, F, H, which makes these components, and B, D, E, I, J, which makes these components. So, there are 3 modules or 3 cells that we make, and the first cell has 4 machines or machine types, which makes 7 components. The second cell has 6 machines or machine types, it makes 7 components. The third cell has 5 machine types, which makes 6 components. So, we come to this solution. Now, after we come to this solution, we also start doing a little bit of capacity calculation, primarily because the given incidence matrix already has the load requirements built into the incidence data. Therefore, we now do the part of the line analysis, we do it in the group analysis and see what is the workload on each of the machines in each of the cells. So, we go back and check that. Now, we realize that first module or cell has A, B, C and G, and now we go back to these components and see how many of them require A, and then add the workload onto A. For example, we have 1, 3, now we look at A in this. So, these are the components that require A, and then we go back to this and see 3, 5, 10, 12, 1, 17, 19, 3, 5, 10, 12, 1, 17, 19, 3, 5, 26, 10, 36, 12 does not require, 3, 5, 10, 12, so 36, 1, 17, 19, 36 plus 10, 46, 46 plus 15 is 61, plus 30 is 91. So, you see that A's requirement is 91. So, we have written A's requirement as 91. 91 means 0.91 of the machine. Like this, we have written all the requirements for all the machines. Now, we want to find out the number of machines that are needed for this. So, now the next table shows the number of machines that are needed. So, 91 we have still said 2 machines of A. The reason is we are now keeping 85% as a realistic estimate that it can handle. Now, let us go back to an earlier discussion. When we started this exercise, we justified by saying that for a 100% requirement of E, there was 1 machine of E. At that time, I justified it by saying that the factor would have been incorporated in the denominator. The availability factor is incorporated in the denominator, but that was for a functional layout. Now, for a cellular layout, I am deliberately trying to create some extra capacity or cushion within the cell by assuming that the availability is only 85%. So, let us stick to this availability of 85%, which will overestimate the requirement in the cell, and that additional capacity will act as some kind of a cushion for the cell. So, if we keep 85% as the availability and do the computation, then we would say that we need 2 machines of A here, 2 of B, 2 of C and also 2 of G, then 1 of A, like that we have carried this out. So, this cell would require 2 plus 2, 4 plus 2, 6 plus 2, 8 machines. This would require 4 plus 4, 8 machines. This would require 1 plus 2, 3 plus 3, 6 machines to do this at an availability of 85%. So, we now translate this into this table and say that when we started the exercise, machines A to J were available. These are the loads on the machines A to J. This is the original availability of these machines. Now, this is the requirement based on our calculation. For example, A is 2 plus 1, 3 of A is required. I have said 3 of A is required. If you look at B, 2B plus B plus B, 4B is required. So, 4B is required. Plus I have added one more of E or G because of the intercell move that we created, that would require one more machine. So, this is the requirement calculation. So, 8 new machines are required if we create. Now, the problem also has another data which I did not mention at the beginning. The problem also says, for example, cost of a new machine can be taken as 20 lakhs, while the cost of an intercell move can be taken as rupees 50,000. So, the cost of new machine being 20 lakhs would give us an additional cost of 160 lakhs, but with no intercell move and with a lot of additional capacity inside. So, one could argue that we have built in a lot of additional capacity inside. For example, one would go back and say that for this 91 there is no need to ask for 2 machines. It is enough if you ask for 1 machine, because it is well within 100. Plus we would have made an assumption that availability is factored in already. Plus, if necessary, a small part of this load can even be shifted to this machine through an intercell move, because this has a lot of unutilization. So, one could do that, and therefore, one can say that I have overestimated the requirement, whereas actually 2 is enough. So, like this one could go back and by the process of creating intercell moves, one could increase the number of intercell moves, and one could say that the number of additional machines required is much less. For example, if we start doing something like this, where we are going to create a lot of intercell moves to balance the capacity, so that we do not add new machines, then the solution would look like this. As I said, from A to A, which means from this A to this A, you can have one intercell move, so that this load becomes less than 85%. So, if you do that, then this will become 71 plus 75, required is 2, available is 2. Similarly, B to B, which means somewhere here I have said 2 plus 1, 3 plus 1, 4. So, from this B to this B, I can send an intercell move and I can reduce 1 B. Like that I can do this. I have shown this in the form of another table, and we can also adjust that F to I adjustment. One could do this, but if we do this, you will observe very carefully that the loads after the intercell moves would be as high as 90 in one of the B machines. It would even be 99 in one of the C machines. It would be 90 again in one of the D machines. It would be total of 190, but 100 plus 90. Together it is okay, and 85 plus 75 is fine. But if we do this process with about 8 intercell moves, we need not have any additional machines, but the cost will only be 4 lakhs, because the problem says that the cost of an inter-cell move is 50,000. Now there are a few other issues, one of which is the cost of an inter-cell move, matching it versus cost of a new machine. Now cost of a new machine has a certain lifetime, so that can be divided as a per year equivalent cost and so on. The inter-cell move cost will be the number of times the inter-cell move happens per month or per year, and then that has to be multiplied by a unit cost of inter-cell move. So there will be issues matching these two. There will be issues related to time and related to frequency of visits for us to match the cost of an additional machine and compare it with the cost of an inter-cell move. Now let us assume that this is an illustrative example which is going to bring out some interesting things by comparing these two. So let us assume that this 50,000 is going to be compared with 20 lakhs, and then on the face of it, a solution with 8 inter-cell moves and a cost of 4 lakhs is certainly desirable than 8 new machines with a cost of 160 lakhs. So purely from a cost point of view, creating inter-cell moves is cheaper and advantageous, but one has to keep in mind that the very purpose of cellular manufacturing is to avoid these inter-cell moves. Now the moment we start doing this, what is shown in this figure, we are actually replicating the old functional layout through the inter-cell moves, except that these machines are kept in different places. So one should also have a solution where we actually create more capacity and duplicate machines and avoid inter-cell moves when we actually create manufacturing cells in cellular manufacturing. So we would propose that this solution of 160, or if this 160 is a little expensive, at least some new machines and very minimal inter-cell move would be a desirable solution that we can propose. We would also look at this example through another solution and understand that we could have different solutions for the same problem. This exercise we will carry out in the next lecture.